let's go over this mini quiz from Unit 7 and 8. So the first question says to calculate the value of the silver concentrate. Just as a reminder, when something is written in brackets like this, that specifically means molarity, which is moles per liter. So that is concentration. It doesn't mean moles, it doesn't mean mass, it means molarity when the substance is in brackets. So calculate the value of the silver concentration in molarity in a saturated solution of silver chloride in distilled water. We were given this information from above. So KSP, let's go ahead and look at what I have written in purple. What I have written in green is the answer you needed to get the points for it. What's in purple is extra, but just for extra explanation, let's look at this chemical reaction. When silver chloride dissolves, it turns into a silver ion and a chloride ion. So on the left-hand side, we have a solid. On the right-hand side, we have aqueous solutions. You must put charges on the aqueous ions in this type of reaction if you had to write the reaction. In this problem, it didn't ask you to write the reaction, but sometimes you are asked for that. In an ice table, it would look like this. Initially, you would only have a chunk of the solid silver chloride, but because it's solid, we don't care about the concentration. You can't really calculate the concentration of a solid or a liquid, only of the aqueous and actually kind of gaseous too. But here we're only looking at aqueous. So initially we have 0 of the silver ion and 0 of the chloride ion. The change is a certain amount that's going to increase of the silver and the chlorine. And so that the equilibrium, they're each equal to X. And that's because we started out with just pure water or distilled water here. And then you drop in your solid crystal of silver chloride and it starts breaking up into ions at a certain rate, which your K value here is telling us that proportion of the products over reactants. Well, here's the K of products over reactants. Because the reactants are only solid, we only have a numerator because products are in the numerator and those are the only ones that are aqueous. So our K value, this KSP here, is the same thing as a KEQ, a KC, a KA, a KB. They're all written as products over reactants. You never put solids or liquids in them. You only use the aqueous and gaseous substances. So KSP is Ag concentration times the chloride concentration, and that's equal to our 1.9 times 10 to the negative 10, which was the value given to us in the problem. So if you just solve, then the silver concentration is just take the square root of your KSP, and it's 1.4 times 10 to the negative 5. All right, the concentration of chloride ion aqueous in seawater is 0.54 molarity. So we still have this same equation here. The molar solubility that I highlighted in purple here means this. Molar solubility is X from the ice table, or from our equation here. Sometimes in these KSP problems, and the letter S is used as the variable, but X is just as fine to use. So if you're trying to solve for X, in this case, since we're given the chloride concentration, that means that the silver and the chlorine are not equal to each other like they were in part A. They are two different values. You already have chlorine from a different substance. It might be sodium chloride, it maybe was magnesium chloride or calcium chloride. Who knows what is in the ocean, but we know that there's chloride ions from this problem. So you set the chloride ion concentration at 0.54. Then you solve the problem with this equation here, and you still use your same KSP value from given in the original problem, or part A, and we have an answer of 3.5 times 10 to the negative 5. That is how much that the silver chloride can dissolve. Now, the chlorine that's coming from the silver chloride also has this concentration, but there was already a whole bunch of chloride ions in the solution, or in the seawater, so we're not really worried about the amount of chlorine that's also coming from silver chloride. That's such a tiny amount that's coming. That's why we only were asked for how much silver was in there. So that's why it's a much smaller amount than the original amount that could be dissolved in pure distilled water. So then the next part just asks you to explain that. Explain why silver chloride is less soluble in seawater than in distilled water. An increased chloride concentration will decrease the solubility of silver chloride, since the KSP is a product of the silver and the chlorine. This is due to the common ion effect. You can also think of it as just an equilibrium or Le Chatelier's principle. If we already have a bunch of this in the solution, in our seawater, then you're not going to get as much to dissolve, and the you can think of the equilibrium is going to shift to the left towards the solid more. So you're going to have a lot more of the solid that's undissolved in the seawater than if you just dropped your solid piece of silver chloride into pure water. All right, next question. Methanoic acid ionizes according to the equation above, and you're given a Ka. Write the expression for the equilibrium constant, Ka, for the reaction. You must include the letter K in this equilibrium expression. You cannot just leave it off because it is in fact a value that the rest of the equation is equal to. If all you put is this equation, that means nothing. What is that equal to? What does that mean? You have to put the K in there. The other thing is that even though we were given a value for Ka here, you don't put the value in there when we're asked for just the expression. To write it properly, you still just put the letter K in there. Sometimes we're not given the K value, but you can still write the expression. You just usually write in the letter K, not the value. Okay, part B says, calculate the pH of a 0.25 molarity solution of HCOOH, or methanoic acid. So let's put a pause here. This equation is a lovely equation, and I know we're all excited to use it, but it is only for buffers. You cannot use this equation to solve for pH or pK in just any situation. You must only use this equation for buffers. Our situation here in part B is not a buffer because all we have is one substance, one acid. It has this concentration. And we're asked to solve for the Ka. To solve for the pH. And we are given the Ka up here in the problem. So what I have written in purple here is some extra equations that I don't think are on your equation sheet. Or if they are, great. You should locate them. If they aren't, some of these aren't. I don't think this Ka one is because that's a simplified version of the Ka equation. This Ka is actually this expression where H3O and HCOO from an ice table, if all you had was you dropped this into pure water, your products, the H3O, oops, did not mean to erase that. Your products, the H3O and the conjugate base, they are going to be equal to each other because you can't get one without the other. As this H falls off, you're left with the same amount of the COOH, the conjugate bases. So that's why they're both equal to X. X is equal to H plus or H3O. A is the concentration, look at that, it's in brackets, it's the concentration of the weak acid, which is right here. So we solve for this problem. Here's step 1, and then step 2, and then step 3, follow that algebra here. Then we take the negative log of X because X is equal to H3O, and our pH is 2.17. Here's the Lewis structure. Part D. This is still part of the second question here. In aqueous solution, the compound HNNH2 or H2NNH2 reacts according to the equation above, and when it dissolves in water, a 50 milliliter sample of 0.25 molarity is combined with 50 milliliter sample of 0.25 molarity of the methanoic acid, HCOOH, and the Kb is also given. Write the balanced net ionic equation for the reaction that occurs when these two substances, our acid and our base, are mixed. So in acid-base reactions, the acid transfers a hydrogen ion to the base. So when you're given an acid and a base like we have, like I wrote in green here, you're going to take a hydrogen ion from the acid and give it to the base. And then rewrite the substances of what they look like after that. And that's it. You don't take any other nitrogens away. When you add the hydrogen to the base, you can either add it to the first set of hydrogens or the second set of hydrogens. So either one, it doesn't really matter, but you should have a total of 5 hydrogens, 2 nitrogens, and the positive charge because it's not just a hydrogen, it's a hydrogen ion. And then your acid should be left with one less of a charge, so in this case a negative sign, and there's your complete reaction. Is the resulting solution acidic, basic, or neutral? Justify your answer. And the reason, or the answer comes from the fact that here's our Kb, 1.3 times 10 to the negative 6, and the Ka that we're still looking at is this Ka up here, 1.8 times 10 to the negative 4. So that means, okay, let's look at the K here. When your K value, whether it's a Ka or Kb, is large relative to another value, that means we have more products, right? Just because of math here. We have more products and less reactants. That means more of our acid, the original undissociated acid or base, dissociated then when you have more products. So let's go back to the question here. Because our Ka is larger than the Kb, that means this solution is acidic. And it's as simple as that. So in another beaker, we have this substance that I highlighted in pink and this substance that I highlighted in green or teal. So this is still our methanoic acid. Now we're adding a strong base, sodium hydroxide. Write the net ionic equation between HCOOH and NaOH. What I have written in purple, you did not need to write. All you needed was the green. But the purple is showing the steps of how to work this out in case you didn't understand how to get to the what I have written in green. So you have your acid. Then you have your sodium hydroxide here. I wrote it as split up into ions because it's aqueous. Only strong acids and strong bases that are aqueous get to be split up in ions. Because methanoic acid is a weak acid, most of it actually exists with the hydrogen connected to the rest of the compound. So we actually don't write it out as broken up into ions when we're trying to find our net ionic equation. So again, here's our acid. It's going to transfer a hydrogen to the base. The sodium ion is a spectator ion, so don't transfer the base or the hydrogen to the sodium ion. Transfer it to the hydroxide. Hydroxide's the base. And that's what it would look like on the right side, on the product side. You have your conjugate base left after the hydrogen was taken from it, and the hydrogen went to the hydroxide to make water. And water is liquid in acid-base reactions. The only thing that is the same on both sides of the reaction is the sodium ion. So you can cancel that. So cancel the sodium ion, and you're left with this. What I have written in green is, again, all you needed. You do not need to show any of the steps for this type of problem. All right, what is the pH of the solution after these two have been mixed? So this is a buffer, and I did not leave enough room for this. But what I have in pink corresponds to my pink highlighted substance. What I have written in teal right here corresponds to the teal highlighted substance here. Just to kind of try to keep things color-coded. We had a volume and a molarity of each of the substances. Find the moles. Ice tables are best when they're written in moles. This ice table is lined up with the net ionic equation. So the HCOOH is in this column, the hydroxide is in this column, the conjugate base is in this column, and we don't have water because water is a liquid. You don't usually include liquids or solids in ice tables. So we have these amount of moles in the pink and the teal. The teal has less, so that's going to completely react. We kind of knew this. That's how we know it's a base. You have a weak acid and a strong base, and the strong base is the limiting reactant, and the weak acid is the one in excess, and that's how you know you have a base. When you mix a strong and a weak of the opposite acid base, and the weak one, whichever one it is the one in excess, then you have created a buffer. So the change value is the amount that the hydroxide had. We had only 0.00875 moles of the hydroxide. That's the change value. We subtract those two from the reactant side, add it to the product side. Equilibrium value is just the adding or subtracting of our values, of our I plus our C. And we're left with an acid, the HCOOH. Let's see if I can highlight that. And we're left with its conjugate base. So that's the other way to make a buffer, is you have an acid with its conjugate base. And that's exactly what we have here. The buffer equation, which now we get to use because this is a buffer, the log of the A minus divided by the HA. The A minus is your conjugate base. So that's this value. The HA is this value. However, look at those brackets. Brackets means molarity. It does not mean moles. You have to divide both of these mole values that we get from our equilibrium ice table by the total volume. So here's the total volume. 50 milliliters and 35 milliliters. So there's the concentrations. Moles, this was from the E from the ice table. Here's the other E from the ice table. Divide it by the total volume, and we have our concentrations now. This is the A minus, this is the HA, to make it really clear. Take these two values, plug them into our pH buffer equation. This is the Ka of the methanoic acid that was given originally way up here. This value right here. So take the negative log of that to get the pKa. Remember the P right here in pH just means take the negative log of what comes next. So pH means to take the negative log of the hydrogen ions. pKa means to take the negative log of the Ka. And then we're going to add that to the log of both of our concentrations here. All right, let's go on to the next problem. The molecular formula of acetylsalicylic acid, also known as aspirin, is this. The dissociation of this is represented by the equation above. The pH of 0.01 molarity is measured to be 2.78. Write the expression for the equilibrium constant Ka for the reaction above. So here we were not given the value of Ka like we were in the previous acid-base problem. So that's kind of another reinforcement of you don't need to have the value. You kind of shouldn't write the value in. Just take your products over reactants, exclude any solids and liquids, and there's your expression. Again, you must include the letter Ka in our expression because Ka is equal to the products over reactants. All right, what I have in purple for part B is not necessary, but these are the equations that you need to know. I really don't think this equation is on the equation sheet, but it's just the backwards of the negative log of the hydrogen ion. Mathematical backwards, if that makes sense. All right, Ka is still equal to x squared over A, where x is equal to H3O. A is equal to the weak acid, concentration of the weak acid, notice. To find the H3O from the pH, you take the 10 to the negative pH, so 10 to the negative 2.78, the value that we were given up here. And that is equal to our H3O. I'll highlight that. That's what I'm looking at. Then plug that into as your x for the Ka equation. So we square that value, divide it by the concentration of the weak acid, which was right here. And we get 2.8 times 10 to the 4. Let's look at sig figs really quick. So this concentration value here is actually 3 significant figures. The 1, and then everything else after. So these 3 are the 3 significant figures. The 2 leading zeros are not significant. They are just place values. Of course, they're important for the place value, but they are in fact just place values. So we got 3 sig figs from this. But then the pH, when you're looking at pH or POH or pKa, only what comes after the digits or after the decimal point are significant. So for some reason, this one's not significant, regardless of what it is, whether it's a 0 or a non-zero digit. So we only have 2 sig figs given to us from our pH value. That way, when we come down here for the Ka, 2.8 is appropriate. 2.76 has too many sig figs. An aqueous solution of aspirin is buffered to have equal concentrations of our acid and conjugate base. Calculate the pH. So here's our pH equation. Take the negative log of the Ka that we just calculated. You can use an unrounded version if you'd like. It probably comes out to be the same answer either way. When you have equal concentrations here, that's just taking the log of 1, which is 0. So we end up with just whatever the negative log of your Ka. So pH is equal to 3.56. But you should probably write out a couple of these steps rather than just writing pH is equal to pKa. Show that you understand that the rest of the equation does include something else and why it is equal to 0. All right, last question. Samples of 3 gases, H2, I2, and HI, that should not be a subscript. That should be a normal I, were combined in a rigid vessel. The initial concentrations of H2 and I2 are given in the table above. The original value for the reaction quotient Q sub C for the reaction of H2 and I2 to form HI before any reactions take place and before equilibrium is established was 5.56. On the following graph, plot the points representing the initial concentrations of all 3 gases. Label, very important point here, each point with the formula of the gas. So let's go ahead and look at this. Q is the same thing as K, or it's calculated the same way. It's just specifically not at equilibrium. In order to plug in values to find a K with products over reactants, you have to have your values at equilibrium, which is why we have to do ICE tables. So we can find the initial, find the change, and then calculate to find the equilibrium. But Q can be at any time. So initially, our Q value is 5.56. So here's our products over reactants. The way I know that this is my product is because the reaction was explained to me this way. H2 and I2 to form HI. Plus, it was also written down here. H2 and I2 forms HI. And there's your coefficient to balance the equation. So we have products over reactants. Q is equal to 5.56. H2 and I2 are plugged in. These are the 0.03 and 0.015 are right here. Now here's the thing. It was easy to assume that HI was 0. And in a lot of chemical reactions, we assume that products are 0. But that's not always the case. In real life chemistry, we often have all three of the substances, whether they're reactants or products, they're all coexisting together in the same container. Plus it says samples of all three gases were combined. So that's how we know HI was not 0 to begin with. We can solve for HI by this. From the ice table, because we had a 2 coefficient, it would end up being a 2x for the change. So then your equilibrium, or your value would end up being a 2x squared because of the coefficient. So you've got x squared. Solve it with math. We've got HI, the little I here means initial, is 0.05. So for this first part A, you just need what I have written in green here, the green dots, and then label each one, HI, H2, and I2. There was, according to the grade rubric, 1 point for the reactants correctly labeled and plotted, and then 1 point for the product of HI because it was required a huge calculation to solve this or to find that initial concentration. Part B. Now we're given the whole reaction. We're also given a delta H and a K value. Look at that. Now we know our K is 49 when it's at equilibrium. After equilibrium was established, the concentration of H2 was 0.02. So immediately you can just draw that. I drew the teal line from 0.03 down to 0.02. But let's go and plug it into an ice table. Initially, we have our values. The change is a negative x on the reactant side, and a positive, or adding a 2x on the product side. What I have written in green for the equilibrium value here is what we're given just in the problem. 0.02 is our equilibrium value for H2. So what I have written in teal then is just solving. So then we know that x is equal to 0.01. So that means I2, you just take your initial minus the 0.01, and then H2, the initial 0.05, then add twice of x, 2x, because of the coefficient 2. So there's our calculated values of 0.005 and 0.07. So that's how we know it does make sense that the reactants should both decrease and the product is going to increase because the reaction is going to be product favored since our K is much larger than our Q. And these are the lines that you should have drawn. When the temperature in the vessel is decreased, this means when we have artificially iced the container, so to speak, does the equilibrium shift to the right, favoring the products, or to the left, favoring the reactants? Justify your answer. So here's a little makeshift chemical reaction that I drew, or that I wrote out here. Reactants turns into products. Because it's an exothermic reaction, the negative delta H means exothermic. It is releasing heat. Heat is on the product side. Heat is a product of this reaction. So when we are icing it, we're taking away one of these products here. Therefore, the reaction is going to want to work to replace that heat. So it's going to shift right toward products as heat is released because this is an exothermic reaction. It'd be the opposite reasoning and answer if this was an endothermic reaction and you were to ice an endothermic reaction. Part D, does the value of K increase, decrease, or remain the same when the temperature is decreased? Well, K can only change when temperature is changed on your chemical reaction. So, because again, we have K is equal to products over reactants, the last part just said that we are shifting towards the products, which is in the numerator of our K, therefore the K expression is going to increase. In the following empty box, draw an appropriate number of each type of molecule to represent a possible new equilibrium at the lower temperature. Well, because we are shifting towards the products, let's count and realize that we've got only 1, 2, and 1, 2 of each of the reactants. We have 2 H2s and 2 I2s. And it takes one of each in order to turn into a product. So let's just go ahead and combine these two here and create two more two more of our products, right? Two more of the HIs, because every time the reaction happens once, you're going to get two products. So because I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to begin with. To begin with, I had 2, 2, and 10. We're going to have this reaction just happen once and redraw it with only one of each of the reactants. This one and this one. And then I should have 12 of the products. The product being HI. And that is it.